Okay, this is a Zeiss Axioplan-2ie imaging upright fluorescence DIC microscope. This happens to be a manual stage. This is non-motorized. If it were motorized, it would have buttons here for the focusing, and all these other controls would be motorized. So everything here is manual, manually operated, a good hands-on piece of equipment. We happen to have this configured for a special application. The special application is going to be high numerical aperture using oil immersion objective lenses. We have the highest magnifications we have are a 63x and a 100x objective. They're both oil, and they are both rated DIC. If you look at these objectives, you can see that they are red letters, red lettering for strain-free objectives. So these are ideal for the DIC. And when we get into the DIC, well, I mean the high numerical aperture, this happens to be a high numerical aperture condenser. Most condensers are 0.9 numerical aperture. This particular one is, there again, this is a special configuration for high numerical aperture systems, high resolution. This goes to 1.4 numerical aperture using oil immersion. So you take your Zeiss oil immersion fluid, and you put it on top of the condenser. We've already done that. And you put it on top of the slide. On top of the slide, so the 63x objective comes in contact with the oil. Then you have this cover slip, then the slide, and below the slide you have another layer of oil before it gets to the top lens of the 1.4 numerical aperture condenser. Right now I've got it on 63x. I do not want to change it right now to a 100 because I spent a lot of time trying to get this image. These are really hard little rascals to see. They're really tiny. I mean, if I slightly even bump my XY, I'm going to blow it way out of the field of view. It just takes a long time to find something extremely tiny, especially when you're working with oil immersion, high power objective lenses. So let's take a look at the screen. So what I have is I've projected everything up on a screen. So this is the Diatom, and you can see the little serrations here on it. This is a live feed at the moment. This is not a digital still. This is a live feed coming right off the microscope. And let me do some adjustments. First of all, this is my analyzer. Okay, let's go back. We're doing DIC at the moment. So remember, I talked about this being configured for high numerical aperture oil immersion. With that, we do have the fluorescence. I have an adapter at the back. I do happen to have the Exfo fluorescence illumination system. This is a fluorescence illuminator. This is metal halide. I don't have the cable connecting. We did all the fluorescence the other day. Got good fluorescence images out of the unit. So let's go back to the DIC. Right now I'm doing DIC. So this is one slide with one diatom on it. Good luck finding that little thing. Anyway, I've got it set at the moment for DIC. And I can adjust my image. Let's see. Just different adjustments I can do here on the image. Any little touch of this is going to affect the image quality. And what you look at is you got your DIC slider. This is a Plan-Apo 63 1.4 oil, Roman numeral 3. And I've got it on DIC number 3. And I'm going to adjust this image a little more here. and I rotate my slider. There. As you see, I'm rotating this is what I'm rotating. I'm rotating this knurled knob on the DIC prism, objective prism slider, and that's changing the shear plane. So as I rotate that, you can see from our image what it's doing. We're going through a pseudo dark field at this point. There's a certain point where you're in midway between a positive and a negative bias that you go through that. I just passed it and now I'm on the other side. Now if I turn this knob way over all the way to the extreme, sometimes you start to lose that resolution. Right in there's pretty good. And you can do different adjustments on this to make this better. Remember in optics you always have trade-offs. So if I try to get a better depth of field, then I'm going to wind up losing resolution and vice versa. So if I want really high resolution, then I need to shorten that depth of field. I can adjust this condenser for my depth of field. I can close it down and give me more depth of field, giving me some more resolution, but I do that at a loss of resolution. I said that wrong. I can close it down to give me more depth of field, but when I get more depth of field, then I lose resolution. I think that's what I said. So I'm just adjusting it, and I was explained before that DIC is like an art. I mean, it is. You just have to sit at this, and it's just like an artist drawing a picture. How do you get a good image? You might sit at this for hours, tweaking this microscope, any microscope. I don't want to talk about this one in general. Any high-end DIC, if it's a low-end, you're not going to get squat. You can be there all day, forget it. You're not going to get good quality, high-end DIC out of something that is not good. But if you take a high-end Zeiss, such as this, you will get good DIC imaging, but even then, you're going to spend a lot of time learning it. You're going to spend a lot of time adjusting it, figuring out the best ways. So I was just showing you some ways that I was adjusting it. Now, I'm going to change a few things here. First of all, this is a zoom. These are super nice. This is a zoom knob. There's another version that is good, but not nearly as nice. It has, this is called an optivar magnification changer. Optivar is a proprietary word that Zeiss came up with. And if you look at my image, you see I'm zooming out. Okay, and then I can zoom in just simply by turning this. The other version has fixed objectives, well, lenses, let's call them, internally. They might have like a 1x, a 1.25, 1.5, 2.5, maybe a 2. I don't know, there's different versions of these lenses that they can have. But this is really nice to be able to just zoom in. These things are hard to find. So there we go. Now that we've got it zoomed in a little more, let's just try some more adjustments with this DIC. There's my pseudo dark field as I'm going through. And let's take it on the other side, going from one bias, positive bias to a negative bias, or vice versa. I'd have to look at a little different cellular structure to be able to tell which is positive and which is negative. On a diatom, they don't show that much. But as you can see, with our with our DIC, we're seeing a relief in here, coming out. The specimen seems to be coming out at us. That's called 3D relief, and that's what we get with our DIC. Now, at the risk of totally losing my image, as I said, this is a tiny little critter, and any little movement there, any little movement, it is going to be gone. I am going to attempt here to turn it to the 100x magnification, and let's see. If I get totally messed up here, we may have to get onto another subject, and that's entirely possible. Okay, can you move that from the view there? Oh, good. Okay, so here we're on 100 power. Now, when the higher power, let's adjust our DIC. Just going with the different biases, looking at how that's shear plane. I'm adjusting the shear. I am adjusting the shear plane. Opening and closing the condenser some. One thing you notice is that part of this diatom is in focus and part of it is not. Well, we're talking about so few microns of a plane, very narrow plane of fields that are going to be in focus at one point. And anytime you're dealing with really high power objectives, that's going to be a problem. You're not going to get everything in focus at the same time. Even in the 1800s, when they were looking at using rudimentary microscopes and they were looking at diatoms, they would actually make sketches with a pencil, and they would make a composite sketch. So it was not what they saw on one particular field. Let me rotate the focusing. It was what they saw on all of the fields. So here's a plane. Now look at this other plane. I'm seeing parts that I did not see before. So they would sketch out everything that they would see as they focus. So let's call that a composite image if all of these are pieced together. Now there are some Z stacking software that we can use with these images, and let's say you take 40 images all at a different plane. Just going like that. Let's say we take a whole bunch of them, we put them as a composite, and you now have one image, everything in focus of the specimen. Video, you can't do that. Video, everything is one single image, and then it's a few milliseconds, and another image is shot in front of your face. None of these are composite videos. Okay, so we've got it on the 100. Let's look at some other features of this microscope. Okay, we have a. Show up here. Okay, so this is the trinocular. This gives me 100% of the light to the camera. This gives me 50% of the light to each. Actually, I think this is an 80-20. So you've got 80% to the camera, 20% to the eyepiece. This is 100% of the light to the eyepieces. That's why now the video went blank. So let's pull it back out. This time I've had it this whole time at only 80%. I really should have had it pulled all the way out for this demo so that we're getting the most light possible to the camera. Gives us a little better image. I should have done that when I set this up. Okay, we've already talked about the zoom. Let's just zoom in on this, zoom in and out on this 100x for a minute. 100x oil. Okay, this is an analyzer. It's a fancy word just for a polarizing lens. I can disengage it. So see, as it's disengaged, now my image is not good. I don't see that 3D relief pattern, and I can even pull out. I can even pull out my. This is a rotatable polarizer. Well, this is the rotation part. I can pull it out. So now I do not have any polarization whatsoever on this optical setup. And as you can see, I've completely lost my 3D relief contrasting on this. So I'm going to engage the polarizer, and I'm going to engage the analyzer, and I'm now back to a 3D relief. Okay, other objectives. We do have some other objectives on this. I'm not going to turn them anymore because I do have dry objectives, and the last thing you want to do is to have oil on your slide and to start to rotate in your dry objectives. These are not oil immersion rated. They should not get any oil on them. You must clean off the oil before you rotate to your dry objectives. Okay, so with those dry objectives, we would rotate the DIC to the proper objective lens whenever it's engaged. All of the DIC objectives, there's several on here, they're going to have their own specific sliders. We have the condenser all set up with Koehler illumination. We do have some filters in here. We have a Koehler illumination field diaphragm. You can hit this 3200K, it kicks it all the way up to the 3200 light, or you could turn it off and adjust it this way. When we're doing the DIC, especially with 100x, 63x, higher magnifications, you're going to want a lot of light. These are iris diaphragms for our fluorescence. You're going to want those all the way up at first, and then after you get a good fluorescing image, then you can close these down a little bit. You can actually center this one. You can center this in the field of view. And by closing these down, you can get a little better depth of field. You can cut out a lot of the extraneous light. So you're dealing with more of a black image, black background with a brighter fluorescing. So, typical 10 power eyepieces, 23 millimeter field of view. I believe we've gone over everything. So this is the Zeiss Axioplan-2ie imaging fluorescence DIC microscope.